Okay, class. So on today's agenda, we're going to get into circles part 1. Now, I know we've talked about circles in the past, but we're going to get more detailed into circles in this section. So on today's agenda, we are going to review parts of a circle that we've reviewed before. We are going to learn some new rules about circles. We are going to do some exercises where they ask us to identify parts of a circle, where we identify kinds of circles, where we determine if a line is in fact tangent to a circle, and we're going to solve for x when they give us a tangent line. After we're done covering all these sections, we're going to work on some exercises on these pages that I'm going to give you. Then we're going to have some homework. We're going to review the homework, and then next class we're going to have a quiz. So let's review some parts of circles that we should be familiar with. Well, we know that a circle has a center, and that's usually what gives it its name. We know that a circle has a radius. We know that a circle has a diameter, which is double the size of the radius. We know that circles can have chords, and if you remember, a diameter is a special kind of chord. We also have tangent lines, which we've discussed before. We've also talked about secant lines, and if you forgot those, don't worry about them. We're going to cover them again today. And of course, a circle has a circumference. Now, in the past, we also discussed minor arcs, major arcs, semicircles, and central angles, but we're going to talk more about those later. So let's take a look at a circle. So here I have my circle. You can see that I have a center here, I have a radius, and I have a diameter. If you remember, we discussed that a radius is the distance from the center of my circle to the circumference. So this circle here has 3 radii. Has a green one here, has one there, has one there. If the radius is the distance from the center to the circumference. So all radiuses have the same measure. So if this radius is 6, they're all 6. Here I have a diameter in orange. And a diameter is a segment that goes from one end of the circle through the center to the other end of the circle in a straight line. And it's made up of 2 radii. So if the radius is 6, the diameter will be 12. The relationship between the diameter and the radius is that the diameter is always twice as big as the radius, or the radius is half as big as the diameter. Let's look at a little bit more detail at some parts of a circle. Here I have circle Q. The name of this circle is circle Q because the center of the circle is denoted by the letter Q. I have a couple of radiuses here. QR is a radius, QS is a radius, and QP is a radius. If we look at the circle as a whole, we can also see that we have a diameter here. PR is a diameter, or if you want to name it RP, is also a diameter. We also have a chord in this circle. Segment PS or segment SP is a chord. The definition of a chord is a segment that touches that touches the circumference in 2 parts. So here, my segment PS is touching my circumference at point P and point S. If the definition of a chord is a segment that touches the circumference at 2 parts, then diameter PR is also a chord. And in fact, when we talked about this before, we said that diameters are special kinds of chords. They're just a chord that goes through the center of a circle. Now, is chord PS a diameter? If you guess no, then you guess correctly. Chord PS is not a diameter because it does not go through the center of the circle. Now, you can see here, I have line K, which is tangent to circle Q. Line K is tangent to circle Q because it's touching the circumference at one point, point T. The point where a line touches the circumference of a circle at one point is called a point of tangency. Line K is tangent to circle Q at point T. Notice that the line of tangency, that this tangent line does not go in the circle. It only touches the circumference of the circle at point T, the point of tangency. Now, if a line does go through the circle, like this for example, well then, line J is a secant line because it is going through the circle. And a secant line will touch a circle at 2 points. So here we have line J being a secant line to this circle, which is unnamed right now. Let's take a look at some other kinds of, some specific kinds of circles. Circles can touch at 2 points, 1 point, or no point. Here we can see circles touching at 2 points. If we look here, we can see 2 circles touching at 1 point. When 2 circles touch at 1 point in this manner, they are called internally tangent. They are tangent to each other because one of the circles is inside the other. So they are internally tangent. Here, I have 2 circles outside of each other but are touching at 1 point. Those are called externally tangent circles. Circles that don't touch at all but have a common center or have the same center are known as concentric circles. So circles that have a common center are known as concentric circles. Here I'm showing 2 concentric circles. I could draw more circles, and if I could draw 3, then 4, and even a big one out here, 5, if all those circles have this point as its center, then they are all concentric circles. Now let's talk about one of the new rules that we're going to learn today. Well, actually, this is not a new rule. This is actually a rule which we've discussed before, but we're going to prove the rule. We're going to expand on the rule today. This rule states that if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. What does that mean in plain English? Well, here I have circle Q, and here I have line L tangent to circle Q at point P. If this line is in fact tangent to circle Q, then when I draw a radius to it, this line will be perpendicular with that radius, making a 90-degree angle. So the rule states that if you have a tangent line to a circle, then that tangent line, if it is tangent, then it will be perpendicular to the radius of that circle. Sometimes they will ask us to prove that in fact a circle is tangent to a line. That a line is tangent to a circle. I misspoke there. Sometimes they will ask us to prove that a line is tangent to a circle. So in this example here, they're asking us to prove that line EF is in fact tangent to circle D. That's what they were asking us to prove. Well, let's take a look here. If this line is tangent to the circle, then it must be perpendicular with this radius. And what I have here now, ladies and gentlemen, is a right triangle. Well, if this is a right triangle, then I can prove it's a right triangle by using the Pythagorean Theorem. And the Pythagorean Theorem states that a squared plus b squared is equal to c squared. We can see here that this is the hypotenuse of my right triangle, and these are the 2 legs. So if this line is tangent, then the Pythagorean theorem will work. Well, let's say that this is leg A and this is leg B. This has to be my hypotenuse. Let's work it out. 11 squared plus 60 squared must be equal to 61 squared. 11 squared is 121 plus 60 squared is 3,600 and 61 squared is 3,721. When I add 121 plus 3,600, I get 3,721, and that is in fact equal to 3,721. So since the Pythagorean theorem works, since these two legs squared equal this third leg squared here, then I know for a fact that line EF is tangent to circle D. Let's look at another rule. Another rule concerning circles says that if two segments from the same exterior point are tangent to a circle, then they are congruent. Let's take a look at an image here. This rule is saying that if segment SR and segment ST come from the same point, which is outside the circle, then they have to be congruent. If two segments from the same exterior point are tangent to a circle, then they are congruent. Well, this looks like it's tangent to the circle. It only has a point of tangency R, and this line looks like it's tangent to the circle. It's only touching at point T, and both these lines are coming from the same point, which is outside the circle, then they must be congruent. Let's look at an example. Here, I have an exterior point A, which seems to be tangent. Line AD is tangent to circle C. Line AB is tangent to circle C. Well, if both of these lines are tangent to circle C from point A, then they must be congruent. And if they are congruent, then we can find X. Well, if they're congruent, then I can set them equal to each other. I can say that X squared plus 2 is equal to 11, because both of these are congruent. With a little algebra, I can subtract 2 from both sides. X squared, these cancel out, is equal to 9. So X squared is equal to 9. Well, I want the square root of X. So I'm going to take the square root of X and the square root of 9. The square root of X squared is X, and the square root of 9 is 3. So X is equal to 3. Let's try some problems on the following pages. On page 599, we're going to do these problems.